So in this topic, what the contact force would be, suppose that there is a table and you place a book on it, and the book weighs, let's say, 6 newtons. So the force table exerts back on the book is also 6 newtons, which is known as contact force, normally represented by capital R and in some books by N. Mostly we'll be using R. And when we will discuss friction, friction is mu R. Mu is the coefficient of friction, where R is the contact force. For example, if we say that we have a surface and you place an object whose weight is 10 newtons and it is given that coefficient of friction is 0.3. So what would be the friction? That would be F equals mu R. Mu is 0.3, R is 10 in this case, and friction would be 3 newton. So if we apply this force equal to 3, the object will not move. If this force exceeds 3, the object will accelerate because we'll be having net force. Let's try some questions. Look at this question number 5. Is it readable? Okay. Question number 5 says, a ring of mass 4 kg is attached to the end of a light string. The ring is threaded on a fixed horizontal rod and the string is pulled at an angle of 25 degrees below horizontal as shown in the diagram, with the tension in the string and the ring is in equilibrium. Find in terms of T the horizontal and vertical components of the force on the ring by the rod. So we know one thing, that is it has a weight of 4 kg. So W equals mg, mass is 4, gravity 10, so 40 newtons. So we add this to it, 40 newtons. Now find the tension. Find in terms of T the horizontal and vertical component of forces exerted on the ring by the rod. So when we split this T into horizontally, that is T cos 25 because it is adjacent to the given angle, and vertically in this case it is T sin 25. So horizontal component on the ring is T cos 25 only, and vertical component on the ring is 40 plus T sin 25. Second part says the coefficient of friction between the ring and the rod is 0.4. So when we consider that friction is applied and force is there, I will be considering, I think, that it is moving towards the right hand side, because there is only one horizontal force which is moving towards right hand side, that is T cos 25. So my frictional component would be facing towards left, opposite to motion. So coefficient of friction between the ring and rod is 0.4. Given that the equilibrium is limiting, find the value of T. So now we can say, if I apply this, friction equals mu R. Frictional force is unknown. Mu is given, that is 0.4. Coefficient of friction. R is basically the contact force. So the contact force in this case is 40 plus T sin 25. Any confusion in this value? Okay, so this is the frictional component, and if we say that it is in limiting equilibrium, the forces on left should equal the forces towards right. So now we substitute friction with T cos of 25, and on the other end we just simplify. 0.4 times 40 is 16 plus 0.4 sin 25, and T was there. So now I just bring all this on one side, minus 0.4 T, sine of 25 is equals to 16. I'm taking out T as common, and I'm left with cos 25 minus 0.4 sine 25 is equals to 16. Use of calculator. Cos 25 minus 0.4 times sine 25, and I get 0.737. So 16 by answer is 21.7. Tension is 21.7 newtons. Clear? So ring is shown, string is light and inextensible. The length is 70 centimeters. A fixed rough vertical wire passes through the ring. The other end of the string is attached to point A of the wire vertically above R. A horizontal force of magnitude 5.6 newtons is applied to the point J of the string 30 centimeters from A and 40 centimeters from R. The system is in equilibrium with each of the part AJ and JR of the string taut and angle AJR 90 degrees as shown in the diagram. Find the tension in the part AJ of this string and find the tension in the part JR of the string. If I say AJ is T1 and JR is T2 and I resolve these two. So this part right here, before we move any further, if we just simplify a little, this is 30, this is 40, this is 90. So when we apply Pythagoras theorem, this would be 50. 3 square plus 4 square whole square root is 5. So this is 50 centimeters. And if I split this, naming it theta 1 and naming this theta 2. So if we split this, may I say that the horizontal component, the vertical component is T cos theta 1, and in this case the horizontal component is T sine theta 1, and for T2, and force is always away from the point. So force T2, this should be T2 cos theta 2, and this should be T2 sine theta 2. Any confusion till now? Okay, now we had some information about the ring. Okay, before that, if I solve this, and let me say we are solving around J, okay? So whatever is the point of consideration, tension is always away from that. So may I say that 5.6 is equals to T1 sine theta 1 plus T2 sine theta 2. One equation, and the other equation would be that T1 cos theta 1 is equals to T2 cos theta 2. Any objection? Now I am going to replace values of sine theta 1 theta 2 and cos theta 1 theta 2. So just looking at the diagram, we had theta 1 right here. So may I say sine theta is actually 40 by 50. Sine of theta 1 is 40 by 50. Simplifying it becomes 4 by 5. So I can write 4 by 5 of T1 plus, and when we solve for theta 2, sine becomes 3 by 5. 3 by 5 of T2 is equals to 5.6. Simplifying it further, multiplying the whole equation with 5. 5.6 times 5 is 28 is equals to 4T1 plus 3T2. One equation is simplified. Now let's do the same for the second equation. T1 cos theta 1. From this very triangle, theta 1 is 30 by 50, which is 3 by 5, is equals to T2 cos theta 2 is 40 by 50, which is 4 by 5. So I'm making T1 the subject. This becomes, we get rid of this 5. This is now 4 by 3 of T2. We can substitute this T1 in the previous equation right here. And that would be 28 is equals to 4. Replacing T1, that is 4 by 3. T2 plus 3 T2. The only unknown is T2. And we can solve for that. 28 is equals to 16 by 3 plus 3 T2. So 16 by 3 plus 3 is 25 by 3 equals 25 by 3 of T2. So 28 into 3 by 25 is 84 by 25, which equals 3.36 newtons. So once we are done with T2, we can replace this value and find T1, which was 4 by 3 of T2. So T1, this equation right here, is 4 by 3 of 3.36. And that turns out to be 4.48 Newton. So now I know T1 is 4.48 and T2 is 3.36. Done with the first part. It says the ring has mass of 0.2 kgs and is in limiting equilibrium on the point of moving up. If it is on the verge of moving up, friction would be downwards. So we quickly sketch this. This is the rod, this is the ring. If it is on the verge of moving up, friction would be downwards. So this is Fr and weight of the ring is also downwards. This is T2, which is 3.36 newtons. And we know all the other things, sine theta 2 and 30, 40, 50, all values. So 0.2 kg makes it 2 newtons. Weight is 2 newtons downwards. Let's fill up the other missing values. Show that the coefficient of friction between R and the wire is 0.341, correct to 3 significant figures. Now we are solving this junction. So when we solve this, we see we can resolve 3.36 vertically and horizontally. And if you wish to use these values, it is already split it in components. I'll do it again just so I don't have to scroll it back. So if we just split this up horizontally, vertically, this was 3.36 sine of theta, whatever this angle is, and this is 3.36 cos of theta 2. So upwards equal downwards. The only upward force is 3.36 cos of theta 2, and there are two downward forces, which is Fr plus 2. And when we solve for the horizontal forces, my contact force would be towards left because there is only one horizontal force which is pulling it towards right because of this 3.36. So towards right is 3.36 sine theta 2 and towards left would be the normal contact force R. So I'm copying this in initial equation again. So this is 3.36 cos of theta 2 is equals to friction. Friction was F equals mu R. So this is mu R plus 2. 3.36, and meanwhile we just substitute these values. So cos of theta 2 is 4 by 5 from the same triangle. is equals to mu is unknown. R is 3.36. Sine theta 2, again from the same triangle, is 3 by 5. Are you following with me? Plus 2. 3.36, I'll share this, times 4 by 5. Simplifying this is 2.688 minus 2 is equals to mu, and 3.36 times 3 by 5 is 2.016. So 2.688 by 2.016 is mu. So 2.688 divided by that was minus 2 first. This minus 2 right here. So this is 0.688 by 2.016. 0.688 divided by 2.016. Mu is equals to 0.341269, and up to 3 significant it should be 0.341. Let's see if we get the same answer. And 0.341, so that's correct. 2 parts done. This also ensures that our first part is correct because we're using the same value of tension we found in question 1. For the third part, additional information: a particle of mass m kg is attached to R, and R is now in limited equilibrium on the point of moving down. Given that the coefficient of friction is unchanged, find the value of m. So a small mass is now attached with the ring. This was the wire, this is the ring, this was 3.36, this is theta 2, everything stays same. Now it is on the verge of moving down. If it is on verge of moving down, friction would be upwards. And why is it moving down? Because a small mass is attached, and that is m. Weight would be mg. Again the same scenario, and we're resolving it. So upwards is 3.36 cos of theta 2, and friction is also upwards, and downwards are two things: weight of the ring and the small weight attached. So this is the horizontal and vertical, and for the horizontal section this is 3.36 sine of theta 2, which should be equal to the contact force. So we replace it again. 3.36 cos of theta 2 is 4 by 5. Let me just confirm that. 4 by 5 plus mu, it says it is not changed, so it's 0.341, and r is all this. This is 3.36. Sine of theta 2 is 3 by 5 is equals to m is unknown, gravity is 10 plus 2. So the only unknown is m. Let's simplify. 3.36 times 4 by 5 plus 0.341 times 3.36 times 3 by 5, and it leaves an answer of 3.375456. Minus 2 is equals to 10m. So even we subtract 2 and divide it by 10, mass comes out to be 0.137 kgs. Okay, question number 9. A small box of mass 40 kgs is moved along a rough horizontal floor by 3 men. 2 of the men apply horizontal forces of magnitude 100 and 120 as shown in the diagram, making an angle of 30 and 60 respectively. With the positive x-axis, the third man applies a horizontal force of magnitude F newtons at an angle alpha with the negative x-axis as shown in the diagram. The resultant of the 3 horizontal forces acting on the box is in the positive x direction and has magnitude 136 newtons. So and find the values of F and alpha. So what do we do? we just resolve them and equate them. Resultant has a direction in positive x direction. That means vertical forces are in equilibrium. So I'm resolving each of them and writing one by one. 100, this would have a vertical component facing upwards. That is 100 sine 30. F newtons would have a vertical component facing upwards. So F sine of alpha, and the only downward component is due to 120 Newton force. So that is 120 sine of 60. So F sine alpha, and taking this number on the other side, subtracting it, 120 sine 60 minus 100 sine of 30 leaves an answer of 53.92. Just for the ease of writing and again I'm taking 54. For horizontal forces, horizontal force towards right is 100 cos of 30. Horizontal force towards right again is 120 cos of 60. And horizontal force due to this force F is towards left, so I'm subtracting it and writing F cos of alpha, and it is already given that it has a net force of 136, so I've just subtracted and added all of them and equated it with 136. So 100 cos 30 plus 120 cos of 60, bringing this 136 on left side and taking F cos alpha on the other side. Use of calculator, 100 cos 30 plus 120 cos of 60 minus 136 is 10.6. So F cos alpha is equals to 10.6. So now we have our two equations, one in form of sine, the other in form of cos. Remember that identity, sine theta by cos theta is tan theta. So what I'm doing is I'm dividing equation 1 by 2. So F sine alpha by F cos alpha is equals to 54 by 10.6. So F goes away with F. Sine theta by cos theta is tan of theta is 54 divided by 10.6. Keeping it as it is, 2 odd decimals, and alpha would be tan inverse 54 by 10.6. Shift tan of answer is 78.9. So we have the value of alpha, and for force you may use any of the equations. Let's use the one which is already visible on screen, that is 10.6. So force is equals to 10.6 by cos of 78.9. Any confusion? This is 55.1 newtons. We could have been doing it directly, because we already know that there is no vertical force, no net vertical force, because it was given that all the magnitude of a resultant is in horizontal direction. So we could have directly done friction is equals to mu r, and net force is equals to friction, because there is no acceleration, mu, and r would directly correlate to the given mass, which is 400 newtons. So you just replace it with 400. Mu is equals to 136 by 400, 0.34.